Hi, this is a video going over how to do the work or start the work, kick off, or at least an example of the work needed to complete regression assignment number 2. So I decided that what I'm going to do is kind of run another example. In class, we did the college scorecard and looked at creating our final preferred model for earnings after college. So because there's only 2 data sets that you'll be working with for the second regression assignment, this first one, which you're seeing the instructions for on the screen, had 3, right? We had the education, we had electricity costs, and we had startups. And then I told you education is going to be right, we ended up doing, it's a simple linear regression. And then we did all that. So then we delete that. And then you're going to work with electricity. And this is the solution file from Brightspace, has everything in it. You're going to pick up here for assignment 2 on regression and startups. And in startups, you have an outlier. And, in terms of that outlier, is an outlier, yes. And in terms of regression analysis, we also refer to it as a possibly an influential observation. So you're going to go through just trying to decide, doing a little sensitivity analysis to decide whether you want to keep it or not. All right, so I thought that to help people who like to have the scaffolding of an example worked out, that I would do a whole new data set called delivery and kind of go through those steps that got me there. This is also sort of a good review for the final. Make sure you are familiar and able to do all these steps. So the first thing here is, let me, and on the final, when I give you a data set, I would define each of the variables so you know what you're looking at. So this is the charge, delivery charge for sending a package. The distance is in miles, the weight is in pounds, and then there's a number of boxes. So it's not the charge for a single box, but for a shipment, you can imagine, from a company to a customer, for example. Okay, so the first thing I'm going to do is just catch us up real quick on the assignment 1 work. And I'm going to not talk the whole time, and I'm going to just start working through it. So I'll try and talk a little bit. So obviously, step 1 I already did. I copied this data set from the chapter 7 data. Now I'm going to start following along with number 2. So I'm going to run correlations on this. So let me do that. Never forgetting that the labels really help the interpretation, are kind of crucial for us. Okay. I don't like the way that looks, so I always change that. I'm looking for anything. Remember, when we're looking for predictors, we have a very low threshold. We're willing to consider many possibilities, anything with an absolute value of a regression coefficient. Remember, this is called regression coefficients. These are called Pearson's correlation coefficient. Pearson's R, all synonymous terms. I'm looking for correlations with our, just be clear here, charge is what we're trying to predict. And so we can call this the response. That's what we're trying to predict. And the candidate predictors are the other data columns that we have. So let's get this straight here. All right. So we see that all of these are greater than 0.5. Okay, but I can't trust those numbers. I have to confirm them with some sort of scatter plot. And just make sure that what I'm seeing does look like it's going on a trend line. So to do that, I always like to put the response on the y-axis. So let me just add a column here. Okay, so I have confirmed now that all these correlations do look like a linear trend. If anything, the trend in the charge, the delivery charge versus boxes could be a little bit, you could almost argue is a little bit up, down, up, down. So maybe not, but we're going to go with it. Again, when we start and we're looking for possible predictors, we always can include anything that looks like a possibility because it will drop out of the model if it's not useful for predicting. So now I'm going to turn all of these into green because right now these all look good to go. Okay, so now I'm going to check for multicollinearity. And we see that these numbers are really low. And so is the 0.12. So I told you when we're checking for multicollinearity, we're very strict. We really, the linear regression, ordinary least squares approach is very robust against mild multicollinearity because to some degree, predictors tend to be a little bit correlated. So that's why we set such a high bar of 0.7 or in absolute value or more. So looks like we have no multicollinearity to deal with here. All right, so I'm going to keep going then. We're going to do the initial full model regression analysis. so there's a table that I want you to create. I'm going to go ahead and do it. So it's going to be called your candidate predictors. This was something we went over in class. I want to make sure I have this here, full model. And then the swap out. And this is where you look for multicollinearity, things that you would, when you have two of your predictors that you cannot include both of them. Let's say instead of 0.08, that had said 0.8. Then I would need to probably check that one and maybe not use both weight and distance at the same time. All right, so this one, we're going to use all three. We've got a green light on all three. There's no multicollinearity. There's no swap out. So just to get us all on the same page, for as an example for other, you know, data sets where you might be doing this. Okay, so we got no swap outs in this one. And you don't need to add, I'm doing this swap out column just to be totally clear that you would need it if you have multicollinearity. And that's what it looks like. And I want that in the video. But for you, if you don't have any multicollinearity, you just can identify the full model. Okay. All right. So now let's go ahead and run that. Remember, the Y is the response. I find it annoying to have this repeated, and I'm not really even using it to begin with. So I just usually get rid of it. We're going to write the regression equation. All right, so that is telling me that the charge dot hat. So this is, I'm saying hat because I can't do a hat like the triangle on top of the word charge. That would imply that is the value of the regression equation. So if you want to simplify it in your mind, the value of the trend line, it was just one predictor. All right, so we're going to have these intercept, and this intercept is a great example, one that's not intuitive, doesn't really make sense. So you don't get money back when you don't have, when you have a package that you don't send anywhere. All right, so I'm going to, sorry, I'm trying to get in here. Let's see if I can copy that into this here. I don't need all those decimals. I usually tell you to go out to 4 or 5 decimals. So we'll just cut that off so it's not so much. All right, so then we're going to have, that's our y-intercept plus our coefficient. This one, again, I don't need to go up that far. I'm going to have to round that, right? That was a 6. And that's times the distance. Maybe this one I'll just type 47, 4, 2, 7. Oops, 2, 7. And this is times the weight. And finally, a $4 increase per box, right? So we'll get to interpreting these here in a sec. That's a regression equation. And we're going to want to write the interpretation of each of the coefficients. So let's go ahead and grab those. And I believe the example I was giving you guys, right? I think I put the units in here too and remind myself. So I have the coefficients, the units, and the interpretation. Okay, so let's do that. So I'm going to actually move this down just one down. Okay. So coefficient. Sorry. Yeah. We're talking about the coefficient for the predictor. For, and so here's the predictor below. Let's do it that way. Units. Right. So the units are always slope units, or rise over run. We don't really have units. Well, the intercept, you can think of it as it's just going to be the units of the response. So this would be dollars. But we don't really need to worry about that one. I believe I actually didn't do the intercept in these, right? Yeah, I did not. Okay, we can leave that out. Let's just leave that out. We don't really need to do that. Distance. So the distance is going to be units of rise. So it's always going to be for the charge. So it's dollars per mile. Dollars per mile. So now we're going to provide an interpretation, and the units guide us as to what to write in plain English. So we're going to say, we're going to look at that coefficient for distance and interpret it as dollars per mile. So the delivery charge goes up by 91 cents for each additional mile to, I don't know, recipient. Okay. Next one, same thing. Weight. So weight, again, is going to be rise over run. So the rise is always the response. So that's dollars per pound. So the delivery charge goes up by, and this is another positive one. So let me just edit this, 47 cents for each additional pound. The, I don't know, order weighs. And then finally, boxes. So boxes is going to then be dollar per box. So it's a single unit always in the denominator of the rise over run. Okay. And again, this one, we can interpret it directly as well. So the delivery, let's just copy it. I don't feel like typing all that. And then we'll edit it. Okay, so in the second one here, the delivery goes up by, again, it's positive. That's why I say it goes up instead of decreases by. So it goes up by $4.47 again. Interesting, right? For each additional box in the order. Okay. So we can, get all fancy here. All right. I think we're all set with that one. Okay, so we did that. Use the regression equation to make a prediction of the response variable of the values of the predictor given and interpret it in a sentence. All right, so this part is the part where I have to make this up now on the fly. So let's just say prediction for order of contained in, I don't know, what do you guys think? 3 boxes, weighing a total of, let me look at what those weights are. Okay, they're decent. Okay, weighing a total of, let's say, I don't know, 53 pounds, and traveling $86. Okay. So the delivery charge is going to then be where we use this information as the predictor variables. So predictor, coefficient, and then the value. Okay. So we're going to grab this information right here. I'm going to copy it here into this little predictor table. So bigger. So this should be maybe, if you want to be clear, if you're learning, you're confused, value of for the predictor. All right, so this is what we're being asked for. So we have now a general equation that can apply, right? So this is our general equation that can apply. So at this point, we're not checking it or testing it. We're just kind of plowing ahead with using it as a tool. And the value of the predictor, let's see, the intercept we're always going to include. And the distance is 86 miles. So, sometimes it's not all in order. You have to read the information given. The weight is going to be 53 pounds, and the number of boxes are 3 boxes in this order. All right. So this is great if you're like managing a warehouse and you're putting together like your average costs. You can gather a bunch of data and then kind of have an idea of what your delivery charges are going to be. So let's just go in here and we're going to say the predicted delivery charge. This is the expected value. And sometimes it doesn't all fit, so let's just put that here. All right, so we're going to use the sum product. So equals sum product. And you don't have to do this. You can type it out all the long way into the equation. That's in yellow right there. But I prefer to use sum product to do that for me. So I get this, and I want to format this as currency because it's the charge, right? It's the delivery charge in dollars. So, you can kind of format this a little bit more if you want. Right, so we have $109.39. Great. All right, so that we have now completed. Now caught us up to where you're going to be when you look at this for the next assignment. So you're going to pick up here. And I thought I had an outlier. All right, so when we look at the regression, there's this kind of question mark right here with this point right here. Right, so that actually is definitely pulling the trend line towards that point. That's an influential observation. So what I want us to do is, you're going to be doing it for startups, but I'm going to do it on this as an example of how to do it. Okay. So the first thing is, in a new worksheet, I'm going to do a sensitivity analysis. All right, so let me just make a copy of where I'm at right now. Move or copy, create a copy, and I'm going to put it here, and let me just call this delivery, rename this essay for sensitivity analysis. Okay, so I'm just going to come in here, and I am going to delete all this. Just delete this. We're going to redo this now in new data because we're going to get rid of this influential observation here. So I'm going to create new data by looking at what is this point. Now notice in Excel I can hover over this, and it's where weight is 183 pounds and the charge was 92.5. So I just spotted it at the top. Okay, what happens if you don't spot it? Well, pretty easy. You go into data, you create the filters, and you find it. Okay, you're like, okay, where is that 183? Oh, there it is. Let me go to that weight because that's like a little bit of an outlier weight, and I kind of want to make sure that that's not overly influencing. All right. I'm going to take advantage of that. Excel's going to change all my graphs on the fly, so I don't want to delete this entire row because notice there's stuff right here. So instead, I'm going to do the wrong thing to do in a sense. I'm going to, first of all, I'm going to copy it. Let's just do a good audit trail here. So over here, let's say, we're going to say, let's copy this here. I think it's there. I think it's there. Let's see what happens. Okay, now I'm going to make this blank. Yeah, whenever you have stuff filtered, it always becomes a big pain to get this right. But you just have to be careful and not do something stupid. So let's just clear that. Okay, so now let's clear our filters, and we see that that first one, everything was there. Okay, so now I want to delete this. You don't want blanks in your data, so I'm going to delete that row. Not the whole row. I'm just deleting those 5 columns and shift cells up. So I'm being really careful not to mess everything else up. All right, so let's just say influential observation deleted. So that we're clear, this is what we're doing, and we're doing it because of the weight. So that was our problem. You can put it in yellow. That's what I was taught you guys before. Okay, so now notice now my weight is much more closely aligned. Right? Unfortunately, I can't trust I've changed now the coefficients here. So let me redo this. So I'm going to, this is, I don't think I'm even asking you to do this, right? It says you don't have to do all the steps, right? You do not need to do all the steps. Just run the regression. Okay, so these numbers are going to change because now there's different data, and we're going to see that the weight, if you reran the correlations, you'd see the weight correlation is going to be higher. I can just see that right off that trend line, that the numbers are tight on the data available. All right, so let's just rerun this. So data analysis, regression, I think that blank at the bottom won't hurt anything, and everything else is the same too. So all good, except let's just put this somewhere where we're not writing on top of anything. So let me just put that here. Okay. All right. So now, oh, something else got messed up. I don't see the problem. Well, maybe it doesn't like the blanks. Okay, at the bottom. So we charge. This one's just going to go to a 31. Okay, let's try that. Maybe not. That'll make it happy. Yep. Okay. All right. So now we run this. Okay. Oh, by the way, I should have said this. Let me back up a second. Should have always checked that this joint significance, right? So this is the joints. Before I did any predictions or anything, this is the p-value of the joint. This is that initial test that you can even trust the regression analysis as being anything you can use. Significant. And good modeling practice. We always check that first. I don't want to skip stuff. I want to get you guys thinking in the right way about these, how to do them. Okay, so that is definitely less than or equal to 0. That's why I did green. That means there are predictors that are statistically significant for predicting the value of the delivery. Okay, so now we're going to do the same thing here. I'm going to check this joint significance. It is still significant, right? Anything that's raised to 10 to the negative 14 is definitely far, far smaller than 0.05. All right, now that we did that, all right, so we have identified that we have something useful in this new model. We are going to compare the adjusted R-squared and the standard error between the full model with all the data on the full model with the influential observation. And we're going to do a little regression table output. Okay, so let's go here. We'll go and we'll say, we'll start with the full model. They're both full models. So let's just say all data is what we're going to, you want to name your models a lot of times, something that you know what was in your model and what distinguishes it from other models. So that's kind of an informal process. It's mainly like you have to understand it so you don't get yourself confused. So the first one I'm going to say is all data. And what we want to do in here is, just that table I showed you in class, predictors, coefficients, and yeah, you know what? I'm going to show you this table anyway, even though what we're told to do in this instructions is to compare the adjusted R-squared and the standard error. I still want to show you how to set up these model comparison table. I think it's easier to have one thing you always do than changing it depending on what you need, if you know what I mean. We're not looking at p-values. We're not modeling. We're not doing model selection yet. So this is kind of set up. So we're going to have the, go to the all data will be here. We're going to come up to the output and grab that information. Put that here. And then the p-values, I think we're going to care about. So we'll put those here. And all of this is so nasty to look at it like that. Makes your head spin. So, all right. So now we have this stuff, and then we're going to get the R-squared, the adjusted R-squared, and standard error, and do the same thing. And I'm going to use my little paintbrush tool. Oh, stop. Okay, so now we got this going. That's what this whole model is, and maybe we want to put a little box around it so we're clear. That's model, all data. Now we're going to do the sensitivity analysis right next to it. Right, so right next to it we will have the sensitivity analysis, where we've dropped that outlier value. And so this part will be the same, headings. And I'm going to copy this stuff down now. And the p-values. And then I'll come up here and get the adjusted R-squared. Oops, did I get them from the wrong one? So you got to be really careful. I should have had the side by side. For all data, I needed to grab these. Careful, careful. All right. Paintbrush, there you are. All right, now I'm going to get those. I'm just going to grab this whole first table, hit that paintbrush, and go to the upper left corner of my new table. And it will instantly format for me. Saves me a bunch of time. All right, so we're going to compare adjusted R-squared. Remember, the adjusted R-squared is coming from the R-squared, which is, it just enables us to compare data. In this case, we have the same number of predictors, so we could actually even use the R-squared directly. They're going to be in alignment. But we want those as big as possible because that's the proportion of variability that's explained by the model. Look at this model. This is what we're talking now, a good model. We're in the 90s. All right, so this is the kind of model that you can trust. So we have 90.5 0.90662 and 0.92230. So this one wins. All right, and now standard error, we want that as small as possible. And the units on the standard error are like, they're going to change depending on what your data is. So that's why you can't really interpret them. It's more they're used to one compared to another. And it's like, think about different golf courses. You want the score as low as possible, but you are going to compare it to other people playing the same golf course and not a whole different golf course. Okay, so this one, we want that as low as possible. These are in alignment. So this is going to be the one we're going to choose. So let's go in here. Choose which is the data to proceed with and why. Okay, so we're going to say we're going to proceed with the data without the influential observation. Adjusted R squared is higher. So maybe I should try and maybe add the nice little word in front. Conjunction, right? Because the adjusted R squared is higher. And standard error. And Excel just calls it standard error. Don't forget, this is the standard error of the estimate, is the official name of this. Because we've been talking about so many different standard errors this semester. Everything has its own standard error. So let's just be clear, the standard, this is the standard error of the estimate. Okay, there we go. All right, so that's my little answer. You want to have something like this that you decide that I can spot. So put a box around it, highlight it, tell me what you're doing, so I don't go crazy looking for it. Okay. All right, so we did that. 1, 2, and 3 are done. So now we're going to start with the full model, and we are going to follow the better model selection logic, which means we make sure we don't include multicollinear predictors in our full model. So that's stupid. Don't do that. So that's the way I showed you, is drop any multicollinear that are strongly multicollinear. We're going to step down and go through a step down process to see what to do. So the next thing we're going to do is we're going to come in here and we're going to begin with this as our full model. So this is going to be now our full model that we're going to proceed with. So I'm going to stay, since I've made the choice to use this data where I deleted, this record right here, I'm going to stay in this worksheet. If you, in the startups, end up going with the original, you're going to switch back to the original and work with that data. So wherever you decide you're going to go, that's where you're going to be doing your step down modeling. All right, so I'm going to work here moving to the right. I could alternatively put all this in a new worksheet, but I actually, I'm just going to kind of keep it in one worksheet right now. Okay, so at least for now, might add some worksheets as we go. But the first thing I want to do is I'm going to look at the p-values. Oh, darn, this is not a step down situation. Look at these p-values. They're all less than 0.05 right off the bat. Well, no wonder that model had such a high adjusted R squared. And by the way, also make sure you can interpret the R squared. So the R squared is like a really big deal, right? So this model explains 93% of the variability in the data and does not explain 7% of the variability in the data. All right, so that's a pretty good place to be if you're going to try to predict delivery charges. All right. So what to do? Okay. Huh. I thought I had one. I was looking for one that had an outlier, and I thought they all in this data set would contain a step down, steps needed. So let me pause. Okay, so I went back and found a different data set, and it has all this. It's healthy living, so it's got a whole bunch of states here, and it's got the percentage of people in the state that are considered healthy. So all of these numbers in this data set are percentage. FV stands for fruits and vegetables. So it's a percentage of the people in that state who eat fruits and vegetables daily. Exercise is the percentage that exercise weekly, and smoke is the percentage who smoke regularly in that state. All right, so healthy is, I guess, determined by a doctor. I'm not sure. We don't have a lot of information. If you were actually doing this in the real world, you'd want to really try to immerse yourself in understanding what the numbers you're looking at mean, because that is huge for how you proceed and what you do. But anyway, so just catch up. I ran a correlation. I identified that all of these predictors in this data are greater in absolute value than 0.15, which is what I'm using as a lenient threshold. Then I looked at the correlations, and while some of these are moderate, none of them are so extremely strong that I would be worried about multicollinearity. So I'm not worried about that right now. And I'm going to proceed. And as I proceed, I check that each of these correlations do look like they're coming from a linear trend. The first one looks decently okay. The second one looks decently okay, and the third one looks decently okay. So really, I should have made all of these green because they're good to go for our full model. And I ran the full model, and I got a overall joint significance. So I know that this model is at least somewhat trustworthy. But then I noticed that there's this influential observation down here on the number of the percentage who smoke cigarettes. So I looked at that, and that's a 8.1, but the healthy associated healthy percentage of adults is only 80.3. So I noticed that. I'm going to run a sensitivity analysis on that. So I go over here. And I dropped that influential observation and took it out of the data set, and I copied it here because you don't want to just mysteriously delete things. Okay. And I highlighted the reason why I considered it influential is because of the 8.1. Okay, so then I run a sensitivity analysis. I also confirmed that it is a overall significant model, so that didn't go away. And then after that, I'm going to create this table to compare the two models. In there, I put in the predictors, the coefficient and the p-value, and the associated coefficients and their p-values, with highlighting. Green means less than 0.05, and orange means not significant, greater than 0.05. Right, then I pulled in the R-squared, adjusted R-squared, and I did my little competition to see which one's got a higher adjusted R-squared. This sensitivity analysis model won, and which one had the lower standard error, and again, this one won. So these were in agreement. So I'm going to proceed with the data without the influential observation, because the adjusted R-squared is higher and the standard error is smaller. And this model, now I can go back and make a statement about what this model's overall kind of ability is. So it's explaining 74% of the variability in the data and does not explain 26% of the variability in the data. But I would not call this my final model because this has got a not significant predictor. So because of that, I'm going to come and do a step down. So for my step down, and again, this is annoyingly in the way. So I'm going to say I'm going to step down and drop FV from the model. So FV is not visible there for some reason. Okay, what is it? Why can't I see FV? All right, I don't know what happened. All right, anyway, because FB is on the outside of the data, so right, remember, let's clear, let's make sure we keep ourselves straight. So this is our response is healthy. We want to predict who's going to be healthy is the goal of this modeling based on these three characteristics. And so these are our candidate predictors. So these three. All right, and then I just copied healthy over here so that I could put it on the y-axis when I did my scatter plots. Okay, so if what you are going to drop is on the outside, then that means I don't have to recopy my data because I can get a rectangle of data for what I want to keep. All right, so let's go ahead and run that regression. So it remembered my response. So the only problem now, it has response and health, so that's not going to work anymore because I messed it up. So let me go ahead and grab it again. So I want healthy. And then I'm going to now do my drop down for my predictor range. I'm going to drop FV from the model, and I'm going to just pick up exercise and smoking as the two predictors, and delete the location, and we're going to put this in this muse spot where we're dropping down. Okay. All right, so the first thing I'm going to do is look at my significance and make sure that that is less than 0.05, and it is. So I have a green light to proceed with this model. All right, so now that I've done the step down, I am going to look at my p-values here, and I don't like looking at them in this format, so I'm going to go to number and go out a few decimals. So wow, really significant p-values here. They're all zeros. So you have to go out, you know, a little further in the decimals to get anything besides zeros, so that means it's highly significant. So now this is going to be, I can actually add that to my table here if I wanted to. So I might as well do that. So let's go ahead and let's call this step down 1, model 1, step down model 1. And what we're going to do is copy the same stuff over. We want the same information in our comparison, our table of for comparing models. So I'm going to grab this data right here. And I'm going to grab the p-values. And I am going to grab the r-squared and the adjusted r-squared and the standard error. And I'm going to copy that down. And I'm going to try to go ahead and keep it there. All right, so I don't know if it'll let me, but I think what I want to do is use the formatting here. And I'm going to go in here and get rid of the highlighting. And let's just do it reasonable. Let's like actually. Okay. So, and we're sort of now said, okay, this was our top contender because we went forward with that, but now we're going to do a step down. All right. So our new step down model is the next contender, right? Taking on the previous contender. So that's where we were at before. So now what we're going to do is we're going to compare adjusted r-squared to adjusted r-squared. This goes up just a little bit. So this actually wins. So let's go ahead and get rid of all this because now we're in the next round of competition. Okay, so in the next round, this one's a little bit higher. And comparing the standard errors, this one's a little bit smaller. So see, when you start kind of tweaking, sometimes these goodness of fit measures only change a little bit. And that's why you need to consider all of them, if you will. We want to make sure that the coefficients kind of make sense from an intuitive point of view. So healthy, the percentage that are healthy go up as the state has a higher percentage of people exercising. And the percentage that are healthy goes down. That's what the negative means in the slope. When there's a higher percentage of people who smoke. All right, so that makes intuitive sense from what we know about how bad smoking is for us. Don't vape. You don't know how much nicotine you have, and it is a very, very hard addiction to kick. So trust me, my husband has had to have his entire jaw replaced. You do not want to be addicted to nicotine. Okay, so that was your public service announcement. Okay, now I believe that I can now declare that this model is the final model because it has got all my predictors are significant. I probably should have done that. Those in green too. Okay, they're all significant. I don't have any more problems, and I'm beating out this inferior model. So this is the one I'm going to declare as my final model. can actually make the same statement now about my final model, because that percentage that I'm looking at here, 73.45. Oh, actually, yeah, I had that as 70. So this is 73.74. This is technically less, right? So it's in a sense, you could overall health, but we don't use that to pick between models. It just tells us in the end how we're doing. This actually went down. So 73% of the variability in the data is explained, and it does not explain 27% of the data. Now, you may say, well, geez, why are we picking this the final model? How did everything point to this? Well, the reason is this insignificant problem with this predictor being included in our model actually kind of threw off these numbers. So again, all these numbers are based on assuming everything is normally distributed, and there's always a little bit of approximation going on. So you really don't fully trust it until you're all set and you have a good, reliable model. All right, so that's how you do the better logic. So if you were to still have p-values that are greater than 0.05, you'd step down again. And it may not be a better model. So, you just want to kind of keep going, and then you want to swap out any multicollinear. And then we're going to make a point estimate. So now that we have a final model, we're going to make a point estimate. And because I'm making this up, I'm going to look at Connecticut here. Let's find Connecticut in this list. Now, where's Connecticut? Oh, there it is. Okay, so Connecticut has pretty high numbers for health. So 89.7 health, and fruits and vegetables doesn't matter. Exercise is 53.9% exercise and 10.7% of, oh yeah, you guys are in Rhode Island. Never mind. Let me go to Rhode Island. Okay, Rhode Island. 87.2. Not quite as good as Connecticut, but okay. So we're going to, let me just make a prediction here. Okay, so if Rhode Island, what were those numbers again? Sorry, I should highlight us. Rhode Island, just to keep my eye on it. Sorry. It's kind of let's pretend we work for the state of Rhode Island, and we believe this model is a pretty good model, and we're going to say, well, we would like to create incentives for exercising more, get more people exercising, and get and keep bringing down the percentage that are smoking. Okay, so let's say what would happen, and so we're going to come before the legislature and we're going to ask for a lot of money to drive these to what we think are causality. Like, remember, this is just showing correlation, but we believe that if we did more appropriate type blind controlled studies, we could show that there is a causality, right? And I believe in the medical literature there is causality has been determined for exercise improving health and smoking reducing health. So based on that, we're gonna figure out the prediction. So what is the expected? So if Rhode Island increases the percentage exercising to, what percentage was it? Sorry, bad. 48, we want to get that up, let's say to 50%. So they want to increase, at least get half the state, the people in the state exercising, at least once a week, and brings down the percentage who smoke to 5%. So you really want to be aggressive and get people to quit smoking. All right, so if that's the case, what is the percentage of Rhode Island citizens that are predicted to be, quote, healthy, however the medical establishments determines is healthy. Okay, so obviously we're asking for a bunch of money here to be able to do this across a whole state. And this is actually the way some public policy gets enacted. People do data analysis and they come up with proposals and they defend it with a data-driven approach. They don't just come in and say, hey, geez, give me a bunch of money because I believe that, you know, going to the beach is going to raise health and I want to get everyone out to the beach. You know, no one's going to be like, no, why? Like, show me the data. Show me where you get this idea. So here we're coming up with this idea. It is part of our current health paradigm that we believe, right? So it's not like a farce. It's not controversial, but whatever. We still want to defend it. So we'd go in and we're going to say, okay, so let's go in and we're going to get a predictor. We're going to get the coefficients. Make sure you can interpret those coefficients, right? So I think you guys are good with that. And then the value, we'll talk through it in a second. And then the value, okay, of the predictor. So let's get these in here. And then the value of the predictor, we're always going to have the intercept. The percentage, we want to raise the percentage of exercise to 50%, and we want to reduce those who smoke down to 5%. Okay, so if we do that, then the predicted percent healthy. All right, so that's going to be equal to some product coefficients times the predictor values. Added each one of those multiplied and then added together, and we're going to get 89.91 or 89.92, close to 90, right? 90%. So that's great. That's what we would claim, that, you know, give us this money, give us 5 years. Let's see what happens, measure it again, and see if your investment was, did your investment pay off? All right, so just real quick, how do we interpret? So the intercept is not always interpretable, but it's a state that has 0% of the people exercise and 0% of the people smoke. So it's not very likely, but if you had to interpret this one, you could kind of interpret it that way. That would be 77.78% of the people are healthy. Now, for each additional percentage of the population that is exercising regularly, you are going to raise the percentage that are healthy by 0.3. And for each additional percentage of your population that is smoking, you're going to decrease the percentage in your population that are healthy by negative 0.58%. Okay, so that's how we interpret it. It's always rise over run. So in our case, the rise is the response, which is healthy, versus over a 1 percentage increase in a 1 unit increase in exercise. In this case, it's a percent, or 1 unit increase in smoking. And again, in this case, the way the data was gathered, it's in percents. So all your interpretation really does go back to understanding what are your units in the data. Okay. All right. So given that, what else do we need to do? All right. So point estimate. Okay. So now I'm going to get into this extra credit stuff. We're going to do a confidence interval and a prediction interval. All right, so in order to do that, I have to, in both cases, I have to get the standard error of the predicted response. Remember, that's that standard error of the y hat at a particular place, and those particular place is here. Those are the values of the predictors. So I'm going to go ahead and do that next. You can stop if you don't want to do the extra credit, but you know, extra credit is extra credit, and you might want to do it. So how do we do this? So we're going to get our data, and we got to center it. Right. So I'm just going to copy this, all of it over, so that I have it somewhere I can easily access it. Right. So I'm going to not need FV, but let me just grab it right now. So let me grab that data, And I'm going to come over here. You know what? I'm just going to put it in a new, I'm going to put it in a new worksheet. So I'll just call this the confidence interval and prediction intervals. Okay. And I got the data here. I don't care about a fee. It was not in my final model. And I got percentage exercises and percentage smoking. And I'm just going to copy this over because this is kind of the part that I care about. All right, so we have our point estimate. We're saying if you trust this data, this represents that you're expected to, if you're able to get the percentage up to 50% exercising and the percentage smoking down to 5%, we expect that the percent healthy will be 89.92. Of course, this is a sample taken at some point in time. So a couple of years later, you can take another sample. People move. Of course, some people are sick and they exercise and they don't smoke and they still get sick, right? This happens all the time. So these percentages are probably going to change. So what we actually want to put is a confidence interval around this point estimate. You'd want to definitely do this if you're going to be proposing and requesting a bunch of money, because people want to know. Anyone who knows anything about statistics will know it's probably not going to come out to that, but they want to have some confidence on what's the range that they could expect if they invest all this money to drive this public policy. So let's go ahead and do that. We're going to, so we want to center the data. So we want to center the predictor values, variables, predictor values at 50 for exercise and 5 for smoke. All right, so let's come in here. We're going to create new variables. So let me grab exercise and smoke. I'm going to copy those. Actually, no, I'm not going to do it that way. Let me come over here, and I'm going to put new data here. So exercise, asterisk, and smoke, asterisk. All right. So those values are going to be the old data. It's going to equal to this old data minus the centered value, so minus the 50, right? So I'm using this value right here, right? And for the smoke, it's going to be the data, observed data, minus the 5, which is the predicted value that I am caring about. Okay, so now that I have that, I'm just going to copy that down. All right, so now I got my data all centered at my new location. All right, and I'm going to run a regression on this because I need to basically run that regression to get out my new centered standard error of the point estimate. Okay, so let's change. So this should be changed. So let's go and grab that healthy data. And let's change our predictor values to these centered values. So remember, it's like we're shifting where the y-axis is. And that's in the slides from 7.1, part 2. And let's put the output range. I'll just put it, I think I can put it here without it overlaying anything. Let's try. I might complain, in which case we got to move it. Oh, good, it did it, even with the annoying stuff on the side. Okay. Okay. So first thing is everything should be about the same. So all these coefficients should be the same, right? So, but the 89.916, right? That's our new, we expect that the intercept now is at our predicted value. So that's a good check that you did it right. All right, so let me just highlight those both in green. Green means go. These are checks that I'm doing. Expect those to be the same. They are. That's the whole purpose of doing this. I shifted everything over. I have the same coefficients as before. That should not change. So we're good there. All right, so all that's good. Now, when we're going to try to build the 95% confidence interval, so let's just go with that, 95% confidence interval around the predicted value. Remember, this is like the value of the trend line, it's a 95% confidence interval around what the predicted value would be of a regression equation. So that's always like kind of like the expected value. If you need to have a visual to guide that, the idea is the value on the trend line. Okay, and so in order to do this, if you recall, we are going to have to get the I'm going to pause and open up the slide to remind you, so you have it straight in front of you, what it is that we need a t statistic and where that comes from and all that good stuff. Okay, so now that we have our data centered, and let's remind ourselves, this is from the 7.1 part 2 slides, where we talked about building that confidence interval around a particular point. And what we said is we are going to start with our point estimate. So for us, this is let me shrink this up a little. This is our 89.92 predicted value. And then we're going to subtract and add a margin of error, which we're going to build using the student's t. So we need the t value from that distribution, where we take our alpha and we divide it in half and we put it on either side, on the outside of our confidence interval, because we want to be 95% confident. So we're going to take the 5% that we're willing to be wrong, divide it in half, and put on each end of the outside of the distribution around the normal distribution we expect exists around our point estimate. And we're going to need the standard error of the point estimate. Right, so we are going to do this to remind you by shifting. So these are the slides where we talk about where we shift everything over to the location of the predictor. And we are now here where we're going to actually build this. So we're going to use this t inverse 2t. All right, so we're going to need to get that t inverse function. So this is the t value that we're going to need, and we're going to get that. We're going to say equals t distribution 2t. And the first thing it wants us to put in, let's go back over here, right, is the value that is going to be split in half and goes in the tail. So because it's 2t, it's going to do the math for us. So let's come up over here and put in the 0.05. And notice it's going to then tell us the degrees of freedom. And the degrees of freedom are n minus k minus 1. And the degrees of freedom are automatically going to be given to us in the residual output. So the total is 49. Let me take that back. No, wait, am I doing this yet? There's 50 observations. So minus 2 is 48 and minus 1 is 47. Yeah, it's the residual is going to be the degrees of freedom in the residual gives you the degrees of freedom needed. So we'll grab that number. And then the next thing we're going to need is this, these two get multiplied together to get the margin of error width. And that is the standard error. And I told you the whole reason we center this is because Excel won't give you this automatically. So this is the key thing we need. So put a big thick border around it, highlight that in, I don't know, I'll highlight it in yellow. That's what we're looking for. That's the whole reason we went through all this work. So we're going to get that the margin of error so what we add to the point estimate. Remember, the margin of error is you take your point estimate and it's a little wiggle room on either side of that value. So our margin of error is going to equal the t value times the standard error. So we multiply those two together and we end up with this number. So our lower bound of a confidence interval is going to be the point estimate. And that you can point to this number up here, the 89.92, or you can point to, it shows up in the intercept. The numbers are the same. I'll point to it up here, minus the margin of error. And then the upper bound is going to be the point estimate again, plus the margin of error. So the point estimate plus the margin of error. Okay. So this is the 95% confidence interval of the predicted value. It goes from, so now we can go to the legislature and we can say that we expect that if we spend all that money to improve health, that in 5 years or whatever, whenever we're going to do a check, it's actually going to go up between 89% to 91%, right? So we could kind of round these if we wanted to. Not that way. I forgot that the numbers are actually percentages already. So let's just go from 89% to 91%, we could say, is where we expect the improvement in the percentage of people in Rhode Island that would be considered healthy would end up. Okay, but what about if you don't, go out and do 5 years out, if you just randomly choose, okay, how am I? Yeah, so that's a confidence loss. So actually, I think I stated that wrong. So let me restate that. Sorry, I want to be a little more precise. And actually, I think some of the stuff I said was wrong. So it's a 95% confidence interval around the overall average in the whole United States if we enact the nationwide, whatever happens. Sorry, if we look nationwide and we take an average and we look at what is the expected value for across the whole nation, all states, if the health was 50 and the smokers were only 5%. And if we, exercise, 50% exercising, 5% smoking, and it's like we're trying to get where the trend line would be or the expected value would be at some point in the future. We, ran this again and where we expect that to be. And it's between 89 and 91%. All right, so now if what we actually frequently are thinking in our head, and that's why I got confused, sometimes you just have to be slow down a little, a little more precise, is the prediction interval. So let me write that out because that's the new one. So this is actually the one that you would say, okay, if Rhode Island is able to reach those numbers, where would Rhode Island be? Okay, not the overall new average taken 5 years from now at that value. Okay, so we are going to use the same t-value, but now we're going to need the margin of error. So let me remind you on the slide for the prediction interval. So the confidence interval, again, is like a new sample. So think somewhere in another snapshot in time, where would we come out for those numbers? That's what we were talking about. And I was saying, well, actually what we usually want is the prediction interval, where we actually want to know for a particular, in this case, a particular state that meets those criteria. So we're going to have this inflated standard error, which will make our margin of error wider, right? So we're going to need to calculate this. So the margin of error term is going to be different. And margin of error, let's put these side by side. We can remind ourselves it's going to be it's going to be the square root of, so let's point to the standard error of the point estimate. That's that number. And we're going to square that. And we're going to add to that the standard error of the estimate, which is up here. And we're going to square that. And we're going to add these together and then take the square root. And sorry, that should have been the standard error. And then the margin of error is going to equal It's the same t-value from the student's t-distribution. So it's going to equal the same t-value we got for the confidence interval, but now we're multiplying it by this larger standard of error. Okay. And then the lower and upper bound are going to be the same calculation. Let me just copy that over here. So let's make sure we're pointing to the right place. So we are going to grab this, go to our predicted value minus this bigger margin of error. And for this one, we're going to grab this box, make sure it points to our predicted value plus our margin of error. So now you see the predicted interval for Rhode Island, all right? If we can get Rhode Island to meet 50% exercising and 5% smoking, is now that we will actually get a health for one state, right? So that's what we're talking about, 1 point. What's the probability? And with 95% confidence, we can say it's going to be between 88% to 92%. All right. Well, we're at right now is 87%. So that's an improvement. I would think you could maybe even do a whole nother regression analysis where you talk about the cost to the state of Rhode Island for healthcare for its citizens, and for each percentage you go up, it's probably several millions of dollars that are saved in healthcare. So, you know, that's how public policy arguments kind of go and evolve. All right, so hopefully that helps you with how to do the rest of this homework. And hopefully what you're getting out of this, like my whole goal besides the technical, like how do you do it, is hoping that what you get out of it is that you are like, oh, okay, this could be really useful. All right. And not that difficult to implement, right? So that's great.